I request everyone to maintain decorum and keep their phones in silent mode.
Good afternoon, everyone. Right, so if you are angry with me, you can tell. Otherwise, whenever I ask, you have to do a little bit of duty, you just respond. So that I know I'm talking to people, not the robots. Okay? Yeah, just joke aside. Right, so thank you for being here to listen to me after having your interesting lunch. I do not know what you had, but I was taken care of well. So thanks to organizers for inviting me here for the talk. And I'm meeting a few of the faces which I know from last 10-15 years, and it is very interesting to see them and learn about their work. So in next 35-40 minutes, I'm going to tell you a few stories which we are following. And from morning, you are, I don't know how many of you attended lectures before lunch. So there were cosmic things, there were word of molecules and strength of different kind of techniques. Now you might find this presentation a little different, but in continuation. So in morning, your director rightly said that there are no boundaries when you go for research. It's only about problem and the solution. Whatever requires, you just do it. If it is about giving a jadoo ki jhappi, you just give it. It's okay. But you should solve the problem, right? So let's see what is there in the pocket. So here, today, the title which I have given to the work, I don't know if you can correlate it with the overall title for the conference or the meeting, but there will be few aspects of it. It is about, you should start from the damaged skeletal muscle, right? So we know that our body is made up of different kind of tissues, and one of the tissue is muscle, and if it is between or it is directly attached to bone, then it is called a skeletal muscle, right? So we'll talk about it, that if damage happened to that muscle, then what can be done, what kind of therapies are available, and what kind of therapies we are working on, and what are the chances of it to be a good alternative to whatever present currently in the market. So I can take you to IPL, right? So Indian Premier League, where you see that some of your favorite players, they are not able to play each and every game. Reason is there is muscle pull, there is injury in the muscle, and it generally takes 7 to 10 days to recover. Why? Because the muscles which are broken, they take a lot of time to recover and create that critical mass of the muscle to perform the activity. What we are trying to do, we are trying to reduce the time it takes to recover from 7 days to 3 days, so that at least you just miss one match maybe, and after that your player is on the ground. So the way we are trying to do it, I'll explain. There are few slides related to the background. So I am hosted in BSBE department, which is Biological Sciences Bioengineering. There is another Mehta Center for Engineering and Medicine, and Gangawal School of Medical Science and Technology. First of all, thanks to people who actually work. I am their representative, and they do the work. I present it and I take input from the audience. I go back to the board, and then we replan things which can incorporate all the beautiful suggestions from audience like you, right? So thanks to funding agencies, our collaborators, and past and present members of the lab. The way we work, this is, we call it theragnalytics. Now you might say that if it is tough for me to pronounce, it might be very difficult for you too as well. Because there is nothing called theragnalytics. It is like self-created, and just to puzzle you so that I can keep you awake. So it is therapy, diagnosis and analytics. I have combined everything, right, to make this very tough word, right? Why that is required? Because in human body, none of the problems are unidimensional. They all are interconnected with so many things. And if we try to solve one problem, then the other one is being ignored, and that creates a bigger havoc. Like from last 70, 80 years or 90 years, we have created very potent drug molecules, but their side effects were not addressed till very recent time. So you might have seen the people who are having cancer, they look weak, they look fragile, but the people who are going through chemotherapy, they look even weaker. Why is that? What is happening? Why that potency is not able to be utilized by the body in very proper way? So what do? We try to control that. There could be any disease, any problem, there will be a lot of things which might be going on beyond the repairing or beyond the curing of the disease. We work on those aspects which are generally ignored. How do we do that? First, you identify the problem as early as possible. In most of the cases, it is very easy to find out if somebody has jaundice, right? Person appears in front of you, your eyes work like a sensor, and they'll tell you, oh, just look at the face of that person, look at the eyes of that person, will tell you that, oh, this person has jaundice. But that was not the primary stage. That is the last stage of jaundice when you are recognizing, and that becomes complicated. But can you do something so that you can recognize at molecular level where actually it is started? There might be some protein which is started malfunctioning, but how would you know? Because that protein is inside the cell. You need some tools so that you can find it out. What we do, we don't go to that initial stage of the molecule, but we go to secondary stage, which is that molecule is being delivered in our body fluids. We collect those body fluids and then we try to check it by using biosensors. Once we know that that disease has started, then we use nanomedicine approach, we use hydrogel based approach or different kind of drug delivery approaches to precisely deliver the medicine at the site. And then we use analytical tools like AI/ML to find out that how best we can utilize the solution to give very specific result, even though the concentration of that molecule might be very low, right? So it enhances the property. So these are some of the examples. These are students who are working. So let's see a little bit basics. So this work today which I am presenting, it is done by Niranjan Chatterjee. He is senior PhD. He just submitted his thesis, now waiting for reviewers' comments. So as we know, this is one of the most abundant organs of the body, which is muscle, right? Almost 40% average body weight, and it is involved in so many activities and all, and any malfunction can create problem for daily activity, and overall it could be fatal as well if it is beyond a certain limit. What exactly happens which makes it function and makes it regular, normal? That is in the concept of the way these cells are generated, the way these cells are maintained. So you know that when a child is born, the body has very limited amount of muscles, right? Because that's what is the requirement. But as adult grows, there are certain mechanisms to improve the percentage of muscle, and then again it goes down with the age. What is there which controls it? So there is something called stem cells, muscle stem cells. So they are the ones which actually regulate the overall muscle mass inside the body in different stages and the requirements, right? So there are some pathways and all, I am not going into the detail, but the important thing is, if there is a problem in the muscle tissue because of any reason, then you have to look for where to hit, right? So first you should know what is the problem. So problem is muscle loss. Then how to improve it? First you need to know actually how it is generated. So if you know how it is generated, then you know which are the spots to work on, right? Like in many of these simulation and docking studies, what basically you look for, that what kind of organic molecule can bind in that pocket to make that protein functional or not function, right? And then you start synthesizing. So maybe in your primary hit you have 10,000 molecules which can do that, but then you narrow it down to find out, oh, 10 they are the best. Then those 10 you synthesize, and then you check into model system to find out that which one is the best, right? So you should know that way to work on. So basically, if you know how to work on muscle stem cells, then you can counter the problem and you can enhance the efficiency. How it can be done? For that, you can activate the muscle stem cells, you can stimulate the proliferation of myoblasts, which are the cells for the muscle, or you can improve the muscle differentiation, which changes muscle cell to muscle tube. So muscles are actually tube-like structure. What basically happens, there are different kind of fibers which slide on each other, and that's how muscles are in stretch state or in relaxed state, right? So basically it is sliding out two different kind of fibers. So either you work at the level of stem cell, or you work at the level of cell, or you work at the level of tube which is generated out of the cell, right? Here are some conventional methods which are used where it could be temperature driven. So these cells can be activated by certain temperature Q, right? So the way you give maybe hint to your friend, okay, just by waving hand or sometimes by some other gesture to communicate a message, same way these cells, they receive certain message by maybe raising temperature by few degrees Celsius, right? That can be done, or it can be light driven. You just give light pulse, or you can do, so here is one example. So here you can see they are using laser, and the way muscle is responding and that connect of nerve and the muscle, that is making that movement of the leg, though mice is in anesthesia condition, right? Then what is our approach? We wanted to work on these different aspects, starting from working on the stem cell up to how to improve the condition of the myotubes. For that, we started with some material which matches in mechanical strength with the muscle. Then we worked on something which actually investigates that what exactly is going on between that material and the cellular system, so that we can understand the mechanism better and improve our product. And then what happens in disease condition. So we tried to work on all these three aspects. How did we do it? So we chose a polymer molecule which is called NEPAM, which is polymeric system, and we tried to include carbon material in this. And what was the reason? Because this polymer is known to be temperature sensitive, right? So what happens at a particular temperature, below that it is in sol or solution phase, above that it is in gel phase, which is a sol gel transition, close to 32 degrees Celsius, which is good because it is below biological or physiological temperature of 37 degrees Celsius, but it is not good enough, because if any change is happening at 32, at 37 you are not going to see the same change again, because now it is just improving the strength of the material at that particular temperature. So we wanted to increase that critical temperature point from 32 to as close as possible to 37, right? It entirely depends on the way side chains of this polymer play important role in making of this network. What did we do? We played a little bit with hydrogen bonding which is happening between the side chains. What did we do? We put a carbon material which is disrupting the chain to chain interaction and enhancing its own hydrogen bonding property, and that pushes the temperature of the critical, which is called as lower critical solution temperature, LCST, close to 36, 36.5. Now our initial intention was that okay, that should be good enough to enhance the activity of the stem cells in the muscle tissue. But we got another benefit as well, and that was the mechanical strength. So we were only looking for that if somehow we can change the solution to gel phase transition close to 37, that should be good enough. But we also found that the kind of network it develops, that is also very close to the muscle tissue mechanical strength. And if there are two materials which are very similar in their mechanical property, the outcome because of the mechanical property will be very similar. So then we found that whenever there is transition from stem cell to muscle cell, the mechanical property of the muscle tissue is very important. If it is not matching, that's why it is slowing down. So in old age, muscle generation is reduced because you will find muscles are not that tight. So in simpler terms, if we say mechanical strength is gone. So one thing, muscle is lost, another mechanical strength is lost, and that's why it is not able to do that kind of regeneration. So luckily, I would say luckily, we found that our system which was generated is matching in mechanical strength, and that helped us designing this injectable hydrogel material. Now beauty of this carbon material was that this carbon material is completely biodegradable. That is a very important thing when you are making any biomaterial. If you have a biomaterial which goes inside the body and it starts accumulating and it stays there, which is that will be harmful for the body, right? So what you want, material goes in, does the job, degrades, comes out of the body along with other excretory materials without leaving any impact inside the body, right? Another second important point was the kind of surface we manipulated on this carbon material, that was similar to the network developed by this polymer by itself. So it aligned the whole of the matrix or the network in such a way as if the two different fibers of the muscle which can slide on top of each other. So material was prepared, characterized by different methods. I will not go in the detail. And then we looked for that how it is interacting, whether these functional groups on the surface of the carbon particle and the polymer chain, they are having some interaction or not. Different kind of characterization methods were followed, and we did find that these are not just two dead materials which are next to each other. Actually they are talking to each other in presence of water. So whenever there is water in the system, they do talk to each other, they are interacting. We also tried to look at that whether that alignment can be seen or not, right? That whether this PAM polymer and the carbon material along with the passivated material, they are making that kind of sliding network or not. And we found that they were, and we could trace it because these carbon particles had another unique property which is called autofluorescence. So they fluoresce. If you excite them at 350, 390, 400 nanometer, they give green fluorescence. So we could follow it. Now you can see bunch of these particles are together and they are making a certain alignment which says that they are actually being integrated in the polymeric system of PAM. Then we wanted to look at in the scanning electron microscopy what kind of network they are generating. You can see the uniqueness of this network, which was only found when they were in interaction with muscle cells. We tried to put some fibroblast cells and they did not create the network. That was very unique thing. Second, we took dead cells and put it there, and it again did not make the network. So we got two information. One, that it is very specific for the muscle-like cells. Second, it is working only with life forces. If system is non-living, it doesn't make that kind of network. Now we got curious that why that is happening, why not, if it is just the material interaction, then it should absorb even with the dead cell and the other materials, but that did not happen. We first tried to find it out that whether that change from myoblasts to myotube is happening or not. So there is a protein which is present when blast cells convert into myotube, and we found these extensions, you can see, that is because of the fusing of the cells. So when muscle cells fuse, there will be more than one nuclei per elongation. That tells that fusion has happened and now converted to myotube. Then we wanted to see that what are the mechanical forces. So we took AFM route, we did AFM analysis of the primary cells, the myotubes and our material, and we found they were very much matching what we initially expected. Here you can see more analysis. The way I'm not sure how clear it is because it's not clear to me, I'm very close to the screen. But anyway, what we found that the mechanical strength was very much matching with the original tissue which we collected from the in vitro system. Then we tried to match the number of ridges. This is another very important parameter, that muscles, because these are bundles of muscle tubes. Now if their morphological parameters are not matching, so it will be like you have many thin threads and there is one big thread in between, so it will not properly integrate. So you need to have the morphological parameters very similar to muscle tissue, and we found that as well. The number of ridges, the difference between the ridges, they all were matching to natural muscle tissue. Then we did more investigation to find out how these cells are merging and converting to myotube. Then we worked with some animal model. That animal model is called DOMS model, and for that we first generated the mechanical injury to the muscle of a rat. If I can play that video. So you can see these rats are running on the treadmill, okay, and we are cruel people, so we make them run for 40-50 minutes and they break their muscles, and then we do some investigation, biochemical analysis, collect their blood, find out what is their creatinine level, and it goes up, which gives the indication that there are broken muscles. And then we injected these animals with our generated hydrogel system. We found that within 3 days there was significant recovery, and here you see after 72 days the biochemical parameter has gone down and generator has also gone down. Right, so till then I can tell the story, right? So this was very interesting for us, that actually the material, whenever we are thinking as a hypothesis of the material, this should work this way, that way, but when it really works, then you need to understand why it is working, because your work doesn't stop there. When as human being, it is our responsibility that whatever we are creating in this world, we should know how to take care of it. Otherwise it will be a menace like plastic. We created plastic, now we do not know how to take care of it, right? So anything you create, you should know the reason behind it, what exactly it is doing in the system. So first we wanted to know that how exactly it is working. So one of the parameter for muscles to be healthy is the cross section area of these tubes is significantly large, but when it is broken, this cross section area drops. But the product which we created, it is called muscalmer, which gives the calmness to muscle basically. So it is again the cross section area is improving, that muscle tubes are gaining their strength. Then other parameters we investigated. Then we wanted to know what is happening. There is something called sarcomere which is present in the muscle. When you do the cross sectioning of the muscle, you see that certain number of gaps are there, and those gaps are sarcomeres. When you go and see the anatomy of the muscle, you will find, right? So we tried to look at, here again it is not very clear, but just believe me, actually it was recovered, right? Then we tried to look at what exactly is happening in, if we check it under transmission electron microscope. So we identified by that method as well that if you do TM of this is very thin sections, we could see intact sarcomeres which were not present in the damaged muscles. Then we did histopathology to find out some of the markers which are present, the way damage to the cell has happened and the way recovery has happened. So in first part we developed the material and we showed it up to the animal level that it works and it takes care of all the parameters which were gone bad due to the damage of the muscle. But remember, this was mechanical injury, right? We patented this technology. Then we wanted to know that what exactly is going on, how it is working, why this material is so unique. Though we had created it, we could have been very biased and we could have said that, oh, because Misra lab has created, so it has to work, kahan jayega? But no, that's not the concept. You have to show it, you have to prove it. For that, we tried to look at that how others have reported. What exactly happens when muscles are damaged and when there is recovery. We found that they say there is something called focal adhesion. So whenever cell is attaching to a surface, there is a connection between the cell and the platform. That point, attachment point, is called focal adhesion. Right, you see focus area, right, all those things. Same way it is for the cell, it is called focal adhesion. We wanted to probe it, that whether that focal adhesion is happening in our materials case or not. So for that we designed new set of experiments. Then we tried to see that what actually influences the focal adhesion, and we found that extracellular salt content that influences it, right? So if there is a lot of salt present in the extracellular space, that can influence the way cells will attach to the surface. So we tried to manipulate it. For that, first we created different kind of carbon nanoparticles. So earlier there was just one type of carbon nano. We created different kind of carbon nanoparticles and we used two salt conditions, KCl and NaCl. So you might have learned in even case of the neurons, it is the exchange of sodium and potassium ion across the membrane which maintains the charge and the migration of the information. We generated different kind of nanoparticles and then we looked for the way they create the network. We found that only certain set of polymeric molecules were creating those networks, rest were not. That muscamer was included in that. Then we did again same kind of investigation on the number of ridges, the spacing between the material matrix. Then we tried to look at the interaction pattern by using NMR. That what exactly the thing which we were presuming that this is because of the hydrogen bonding and there is interaction, which is actually happening or not. We did find that okay, there is a role of hydrogen bonding which is initially between the chains, and now after introduction of carbon particle, it is the carbon nanoparticle which is dictating the terms for hydrogen bonding. So these are different models created by Niranjan. It took a lot of time for me to understand what he has created. So I'm not going to explain to you, just believe me that this is how it works, right? Then we looked for different kind of attachment experiments where there is something called vinsulin, which is one of the proteins involved in this focal adhesion. And we found that in case of muscapar it was much higher compared to any other material which we used. Then we used crown ether to extract all the potassium ion from the system, and we tried to see that in that manipulated system what is happening, and we saw that all the cells, they started detaching from the surface. And then we added our muscamer and we saw that again attachment is starting. So this is called a negative way of doing the things. Suppose you do not know that a particular gene is responsible for its function. So what do? Either you knock out or you knock down, and then you see that what kind of effect it is putting on attachment property using AFM. Again we got that it is actually enhancing the attachment and the mechanical property. Then we did some other different kind of myo-D1, which is a protein involved in structural integrity of the muscles, and we found that whenever there is muscarmor, actually it is enhancing the percentage of that protein. So finally we could confirm that it is actually the focal adhesion which is playing the role. So if there are damaged muscles, then you are putting this material, it is making a network which is integrating in between the muscle fibers and helping it to improve the focal adhesion at higher percentage, at higher number, and that helps in final conversion of these myoblast cell to myotubes, which actually improves the health of the muscles. But these all were done in normal condition. Now if there is disease condition, so we know that for many of these diseases, research is going on for the therapy from long time, but we are failing. Why? Variability in human system is a lot, right? So that is the difference between a solution which you have kept in a test tube and the solution which is present in your body. Because the complexity, the variability, it will be a lot. In a tube, whatever you put, that might remain as such if they are not reacting or there is no product formation or the byproduct formation, right? So because of that variability, even though you know that your material is doing mechano sensation, it is doing the mechanical adhesion and it should improve, but it might not happen because during disease state, some molecules might be released by your body which can neutralize the effect of your material. So we want to know whether this material will work or not. So for that we chose a condition that is called cachexia. So cachexia is muscle loss during cancer development and during chemotherapy, which is the process of curing cancer. So for that we first try to understand that what exactly happens, and then we try to develop a material which can deliver a drug along with giving the mechanical strength. And that drug we chose, which is called niclosamide. This drug is already available in the market, but it is used for killing worms inside our stomach. Now we are utilizing it as anti-cancer because we got to know among many pathways which are active in cancer cell to make it survive, that is called phospho-STAT3, and we wanted to stop that phosphorylation of STAT3 protein, and niclosamide is actually one of the drugs which can do the job. So we chose this drug, and now we had to entrap it in compartment which delivers only when it is required. Otherwise again the same problem of the side effect might arise. So what did we do? We created a nanoparticle system which is very sensitive to ROS species, and whenever there is muscle damage, many ROS species, reactive oxygen species, are generated and they can cleave only certain bonds. So here we are trying to use selenium bond, which is very sensitive to ROS generation. And now whole structure of nanoparticle, it depends on whether that bond is intact or that bond is broken. If bond is broken, whole system collapses, and during the collapse the drug slips out and goes in the tissue. Till the time there is not sufficient ROS, it will remain as such even if you inject into muscle. So whenever there is higher cycle of ROS production, more drug release, less ROS generation, less drug release. So we could control it, we did characterization and all to find it out. These are the nanoparticles which were created, loaded with the drug, and we tried to see the sensitivity using different kind of controls where you use ascorbic acid and hydrogen peroxide. One is ROS generator and another is ROS scavenger. Again, whenever you are planning an experiment, you have to have positive control, negative control, and something in between, right? So that you know whatever is happening, that is happening because of certain thing, right? Then we did the release study, and then we did encapsulation, and now we developed an animal model which has tumor. So we injected cancer cells inside on the back of the mouse, and once tumor were of certain size, we started injecting them with our formulation, which has musk armor as well as that nanoparticle with loaded niclosamide. And we tried to follow that, what exactly is happening. And we saw that both are playing their independent role, their additive role, and there is something called synergy. So when there are two items working on same problem and their outcome is not only just addition of A and B, but beyond that, that is called synergy. So we found that mechanical forces were helping in generation of the muscle. Also, drug was trying to control the loss of the muscle because of the cancer which has been generated. But when both were together, improvement was much better, right? So that's called synergy. We verified it. Now there is something called strength test, which is called the functional test. So what did we do? So you can see that a mouse which is hanging from that lid of the cage, and we note down the time, how long it can hang. So if you have strong muscles, like for human being, they can hang for a long time, right? If it is not that strong, then they will be falling in certain time. That time is noted, and that is called latency to fall. And then you note down the time, it is sometimes in seconds, sometimes in minutes, and then you compare. So normal, disease and recovery one, and the normal and the recovery one should match the time, and we found that was very much matching the time. So it's not only that it is happening at the sarcomere level, or it is happening at the mass is increasing or cross section area is increasing, but the function is also increasing. So strength is coming back even in the condition of cachexia, which was a disease condition. And then again we did the multiple testings, right? We also tried to find out that what is happening to this material inside the body. So as I said, then material should be biodegradable, that once job is done, it degrades, it comes out of the body. So we tried to look at that what is happening to this material. So we collected the urine of these animals, and then we did testing, mass analysis, LCMS, different modes of finding out that if there are traces of this molecule present, and we found that they were only in those biofluids which are excretory in nature, not in the tissue. So we took the tissue as well, we did the homogenization, collected the biofluid, and again we did the testing. So that's how we got to know that this material comes out through urine, which is a good thing, that once job is done, it will be cleared off. Then we did safety analysis by using the tissue imaging and all. So what we can say that the material which we have developed, it has multiple properties, including it can improve the proliferation and differentiation, making of the muscle tubes as normal as possible, and faster recovery time in both mechanical injury condition as well as the condition of disease, which is here we have chosen cancer, right? So this is the network which we got serendipitously. It was not planned. We had just planned that we'll have a carbon material which will change the LCST temperature from 32 to 35 or 36, and then job will be done. But when we started working on it, so whenever you take any project, the most important thing is observation, not the final result. You should observe each and every change, what is happening in that material by whichever way possible, by some characterization methods, by some functional assays, and then you might notice something which you would not have expected, and then you come up with a new theory or a new product or new biomedical product, which happened in our case, right? So these are again, right? Now what is the next thing, right? So I started my talk with saying that, oh, it could be good for some sports person, right? But you know that in sports, right now the biggest problem is doping, right? They are being disqualified, this and that. And one of the tests they do, they check in the muscle area if there are some injection points. That is the first point. Now all material is being injected. So how the authorities will know that it is not some drug? So we have to move away from it. Second problem is that when you are injecting it, you are targeting only one tissue, one place, but muscle loss is from whole body. How your material will reach to each and every site. So you have to make something which can be applied from outside. That is called transdermal. So you apply on the surface and then by itself it penetrates through the different tissues and reaches to muscle. So that is our future goal. We are trying to make it transdermal. Then you look for a few more proteins and all, because as I said, most of the products we make, we just unidirectionally we think, oh, it will be beneficial for this. But what it is doing to kidney, what it is doing to heart, we do not know until we are very sure that to most of the critical systems it is very benign or non-effective, then only it will be approved for clinical trial. So we are working on that. Then we can use it for some other conditions as well, which are age related. So there is a problem which is age related called sarcopenia, where lot of muscle loss is there in very aged people beyond 70-80 years. They lose a lot of muscle and that's why their daily life is affected. So if we can improve their condition and then combine it with gene therapy for some rare conditions. So because it is able to hold nanoparticles, those nanoparticles are loading nucleosamide, can we tune it to load some gene sequences? So we are working in that direction. So with this, thank you very much for your kind attention.